Continuing on with the PDF, the next thing it asks is, why is this solution, this makes it look a bit complicated, this makes it look a bit tidier with the unit step function notation, but why in particular after the step has come and gone, why is it of this simple form? And that really leads us to a very different way of analyzing it, which in most ways is more powerful, at least for linear equations, than the step-by-step progression in time method that we did. So we want, let's say, just for a notation, let's say y1 of t is the solution to a slightly simpler problem where I have that same force and then I turn it on at A and then I leave it on forever. Okay. Well, the hint was you shouldn't have to do any work to solve this problem because it's identical until A plus delta t to what we already saw. Instead of turning off, it just keeps going. But we just wrote down the solution to this. Okay, and so that's our master factor for the amplitude, and then 1 minus cosine omega t minus a, and then times, this should only start being active at a. Okay, so factor, interesting function, and then thing to turn it on at t, turn it on at a, and then nothing to stop it. Okay, now I then ask, what about, let me call it y2 to distinguish it. Let's say that's the solution to the problem, where instead of doing this, we wait until a plus delta t, and we go down. I really should dot these, of course. They're not really part of the graph of the function. Dot, 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 dot. And then have a negative step function, minus same magnitude. That's an h, right? Okay. Well, this is the same problem. It's with a minus sign, and I'm just delaying it by delta t. So it's not much harder. It should be minus j over m omega squared delta t, 1 minus cosine, same angular frequency. Now, of course, the a is changed to an a plus delta t, and then we only turn it on at a plus delta t. Okay. So, why is this so interesting? It's because of linearity. That this is a linear differential equation, and my claim is that if we add those two functions together, we solve the problem we're really interested in. Okay, let's let y3 be y1 plus y2. Okay, then I don't really have room to keep y1 and y2 on here, but it's okay. You can always rewind, and we'll see them again in a minute. Let me go through this real carefully. Hopefully you've seen this if you're coming from the background that I'm expecting with ODEs. But it's so crucial. It's one of our big themes, linearity. Let's plug that into our differential equation. And somebody asked, in one of the comments already, asked about doing fluid flow, for example. Fluid flow equations, any realistic fluid flow equation, is nonlinear. And that's super cool and important, but I'm really going to focus much more on the linear types of mathematics, really. Okay, so I'm just going to plug that definition of y3 in here. And then the key is all I'm doing is taking derivatives, which is a linear operation. Derivative sum is the sum of the derivatives, multiplying by scalars and adding. And so I can regroup it as this same operation, this same combination of y and its derivatives applied to y1. I'm going to put in a somewhat unnecessary parenthesis for emphasis. Okay, and now what is that? This was designed to have the right-hand side. This is equal to j over delta t ha of t. And this was designed to have the opposite sign, a step function that turns on at a plus delta t. Well, that has a common factor, and then this common factor of j over delta t times the difference of step functions. And in the introduction of the PDF, we know that that's just a really good way of creating the rectangular pulse. It's the definition of the rectangular pulse. Okay, and so because the rectangular pulse, the input, this guy, is equal to a turn-on pulse that you leave on forever plus a opposite pulse that you turn on later and then leave on forever, and then they cancel it after they've both been turned on, then that's going to say that the solution to this problem, which seemed complicated and seemed like we had to do it in these 3 parts, we actually do something that's a much easier 2-part solution, and then it's delayed and flipped version, and then it's just the sum of those guys. And so that's why the punchline, of course, is that this is just that master factor in front, and we're getting kind of bored with, to be honest, kind of sick of, times, and then there's that 1 minus cosine omega t minus a, turning on at HA, turning on at A, plus 1 minus cosine the delayed start and turning on then. Okay, let me actually have it on the board here. Linearity. The idea that if we can solve 2 simpler problems and the problem that we have is the sum of those 2 problems, then the solution will be the sum of the individual solutions. Not true always, but super powerful when it is true. Ooh, one thing I forgot to check, I think I put it in my cheat sheet, is the initial conditions. This would totally not work, except that the initial conditions, it's really linearity, and it's specifically homogeneous linearity. If we had any kind of inhomogeneity, this would screw up, but the initial conditions are fine. It's true that y1 of 0 is y1 prime of 0 is 0, and the same thing for y2, and the same thing therefore for y3. If we wanted to solve problems where the initial value of the initial displacement or velocity were non-zero, that would screw us up. It wouldn't be impossible to salvage still a fundamental principle, but really, when you're looking at linear equations, you only get the full power of this kind of thing if everything is nicely homogeneous. Okay, so the stuff that we weren't trying to bring into the problem, the initial conditions, it was really crucial that those were all 0. Because we really should always check those, of course, or else we're not really solving the correct kind of problem. Okay, so the punchline here is that linearity is the reason why this turned out to be so simple, and this would have been a much better way to do it in the first place. But I really do like leading people through ways of doing things that are more intuitive or more sort of the naive way of doing things, and then only later maybe using the solution as a hint as to, wait, could we have done this in a cleverer way? If I always show you the absolute cleverest way right from the start, you're not necessarily, I think it's not as good. Okay, so let's continue into number 2. Wow, we only got through number 1 of the very first handout. That's okay. So part 2, the simple hammer. So with a little bit of a change in notation, hopefully it's not too confusing, we'll denote y sub a of t. Now that's that time value. Okay, that's the solution to ya. Its property is that this guy, I don't really leave room here. No, I think I've got enough room. J over delta t. That's not really, sorry. Change my mind again. J over delta t. And that's the rectangular pulse starting at A and lasting delta t. And I want this A is going to match with this A, okay? And so I want to emphasize that if I change this value of A, if the pulse starts at maybe a later time, but let's say the same width for simplicity, we'd like to relate the solution that comes from this impulse to the solution that comes to this impulse. Hopefully physically it should be pretty clear what should happen. Again, because the initial conditions are 0, it doesn't matter how long I wait. It's just sitting there. It doesn't matter how long I wait. If I hit it at A or if I hit it at B, it's going to do the same thing. But in this case, if B is bigger than A, if it's later, it's going to do the same thing, just delayed. Delayed by how much? Going to delayed by whatever the difference is, B minus A. So what that says mathematically is that the solution from if I hit it at time B, for a length of time delta t, should be the same solution. And then how do I translate? How do I slide a solution over? What you always do to translate functions, what we teach in like algebra 2 of modifying functions. Just slide it over by that time delay, b minus a. Okay, so that's the sort of a physical intuition argument for why this should be true. Okay, and it's, I don't know, it's a pretty ironclad argument. If this didn't fit with what we just wrote down as our solution, then our solution would probably be wrong. This is a really good argument. So let's just look. Let's just write this down and see if it collapses to y b of t, of t minus b minus a. Okay, so remember it's our factor 2 times the 1 minus cosine. And the point is that everything's just of the form t minus a shift that exactly depends on the starting time. Oh, and now I'm putting in t minus b minus a. So I'm putting in exactly what, that's a b minus a, hopefully you can read that, times HA of, I'm going to need more room, times HA of t minus b minus a. Okay, and then minus the 1 minus, I'm going to just, and then this is HA plus delta t of t minus b minus a. So I'm taking that big nasty formula from just a minute ago and shifting things. Okay, but what happens if you have t minus the quantity b minus a and then minus a? The a's cancel and you just get t minus b. Voila. Okay. Similarly here, h sub a, that's really the unshifted unit step function, the one that turns on right at 0, of t minus b minus a minus a. The a's cancel, you get t minus b. Oh, okay. H of t minus b is just h sub b. So this becomes h sub b of t. Okay, I don't want to really want to write this out because it's not, the point is not so much the exact manipulations and everything. It's that this was all based on functions that were aligned to a. If I shift it by the difference, it'll be aligned to where t equals b. Okay, and so indeed, this just does collapse just to y sub b of t. Okay, and the point I want to make, the overall point, kind of hand-wavy, vague point at this point, is that this is a symmetry principle. Okay, that the system is, the way we would say it, is symmetric. Symmetry sometimes suggests like mirror symmetry, like just around, like across an axis, but it's a much more general principle. It's that you can do something systematic to the system and it doesn't change. It's symmetric under translation in time. So that when you hit it like this, here's the F, the Y response looks like this. Then if I hit it at a later time, it doesn't do exactly the same thing as this. And it's not literally exactly the same function. It shouldn't be. It should modify, but it modifies in exactly the same way, in a systematic, predictable way. That no matter how much I shift this guy from A to B, shifting by B minus A, it's going to do exactly the same thing to this. It's just going to be shifting so it turns on at B instead of at A. Okay, and this is an example of a symmetry property, that the system itself is symmetrical, so that when I shift the forcing, it does only the simplest kind of shift in the answer, the response to the forcing, that it could possibly do. This would not have been true if we had started with a non-zero initial condition, because with a non-zero initial condition, suppose I start out like this, it's going to depend on exactly where in that cycle, that original cycle of oscillation coming from the initial condition. Oh, that's not going to cycle around here like this. It's going to depend where I hit it. If I hit it on an upswing or a max or a downswing or whatever, it's really going to matter. That breaks the symmetry by saying something happened at time 0, period. And then you've got to respond to that. But because nothing was happening to start with, the system is really symmetrical. It should be, and again, the physical argument is pretty good. You're looking at a system in equilibrium that's not doing anything. Wait to do the experiment for 1 hour. You're going to get the same result. Very basic principle of symmetry under time translation. Okay. And then another big principle that we've already seen is, and I think this will be the end of the video, this video. Okay. Let's make the response a little bit more complicated. Again, for simplicity and sort of homogeneity purposes, we're hitting a system that wasn't started out doing anything, okay? But we're hitting it with 2 pulses, like here, and we're going to go ahead and have this have an area inside it, the impulse be J1, and then later, maybe a bigger impulse, J2. So this height is J2 over delta t. And just to be simple, we'll have them have the same width. Not super essential. But I kind of want to leave that width to be the same. Okay. And so in other words, f of t, as it's shown in the handout, it's a rectangular pulse from A to A plus delta t with total area J1 plus 1 at B from B to B plus delta t. And I've drawn it in a way that makes clear that it's a pulse and then stop and then start again, so that B is bigger than A plus delta t. And it's very reasonable. If we look at the way we solve this, sort of progressing in time 0 and going off forward in time, that it might be rather different if these pulses actually overlapped. If it was like this, turn this on, then both of them are on, oh, and then only the strong one is gone. That looks qualitatively quite different from here. Okay, but and you totally could solve this as a 1, 2, 3, 4, 5 piecewise problem, but that's the wrong way to do it. We already know, we've already seen the power of linearity here, that if we know how to solve this problem with 0 initial conditions, okay, that solution is, and the notation's a little annoying because I have this J1 here. Let's say, I apologize for switching notation in the middle. Let's say YA is the solution with F, let's say it equals normalized to 1, let's with the impulse be 1. And so then I can put in the J1 as an artificial factor, okay? And so this is, you start the impulse at A, it lasts delta t, and it has total momentum transfer 1, okay? Then the solution, if only this were acting, that would be your solution, times J1. So the solution would be Y equals J1 YA. Okay, you just scale it up to get the right factor. And again, because you have 0 initial conditions, that's not going to be a problem. You can scale and add those, and they're not going to give us a problem. But then plus, what about if only this happened? If only this happened, you get a solution, J2 YB. And because of linearity, if you put this combination into m y double prime plus m omega squared y, you're going to get out the sum of this and this. Okay. That's pretty awesome. It's a superposition principle is another way that physicists say it. Superposition means that you solve simple problems and the answer to the complicated problem with a sum of 2 influences is exactly the sum of the solutions to the individual problems, or the appropriate linear combination. That if y sub a works when this is just a 1, then you just scale it up by appropriate factor. That's already a pretty important principle and doesn't work for nonlinear phenomena. Okay, so that, actually let me go a little further. I just want to get the punchline here. Okay, so, and in particular, that works even for this weird case where they overlap. Looks different, but it's still going to work exactly. Very nice property of linearity. Okay. The next part is really exactly the same thing, but with a sum of more than two things. Okay. If we have this be the solution for a little rectangular pulse, now suppose that my forcing function is a little rectangle and then a bigger one, bigger one, bigger one, and then smaller, and then bigger, and then smaller, and they all have width delta t, although that's not really crucial. Okay, I can just divide it up into a bunch of little rectangular pulses. And suddenly I've got something that's pretty general that can approximate, I think, pretty well a fairly general forcing function, even though we started with a super simple forcing function. Okay, if this f is the sum of, let's say, n equals 1 to big N of j n over delta t r a n to a n plus delta t of t, okay, just the sum of all those guys, then the y by linearity is going to be exactly the same sum. It's just going to be that same factor, jn times y, starting at a sub n of t. So just solving this little problem of the rectangular pulse, which in itself is the sum, or the difference of this and then a delayed rectangular pulse. But let's keep it as the y is the solution of the rectangular pulse here. Just knowing that solution, which is fairly simple and predictable, allows me to suddenly do a pretty decent approximate solution for a very general class of functions. And we're going to take this very, very far. This idea that linearity, it's really using linearity and symmetry. There was nothing special about any particular a value, any particular time value. If the a gets delayed, the y gets delayed. The way this function depends on this parameter is super simple. That was the symmetry principle. And then the fact that I can combine all these together into a much more complicated object and get a very, no more complicated solution, a very predictable solution, is super powerful. Okay, that's a good place to stop.